Thank you very much for that lovely introduction. And now that you can hopefully see my slides, so I'll tell you a little bit about myself. I'm the co-chair of the LSST Solar System Science Collaboration. So that means part of my job is as community service to help engage the planetary astronomy community in getting ready for this fantastic telescope and survey that's going to be coming online hopefully in about 2023. And so I'm sure you've heard a lot about the Legacy Survey of Space and Time, but probably not a lot about in terms of what it's going to do for solar system astronomy. So I want to take one step back and ask, why do you study solar system bodies in general? And the reason we do this is really because this tells us about how the solar system forms. Small bodies and planetesimals are the building blocks that formed our planets, and they're the remnants left over. And so my analogy is that the orbits of these objects and their properties are like the broken glass and fingerprints after, left over at a crime scene. It's how we piece together how the solar system formed and evolved. And it's these bodies that are telling us a lot about how the giant planets have moved around, how do we form planets, and even now that we're able to do comparative planetology, even with small planetesimals, with having planetesimals from other solar systems pass through ours. And so it's really important to study the small bodies of the solar system to really be able to understand our solar system's history. And then we know of about over 4,000 extrasolar planetary systems. This best one we're ever going to be able to study is our own. And so it's really important to be able to study these small body populations. I love showing this slide because, when we talk about finding moving objects, we rarely show actually how we do this. And it really is, as my mom has said when she asked what I do, it's find the moving blob in the image. And so if I can point this out, right, let's see if this is going to work on my iPad. I think it will. That this object here that you're seeing, this is actually Eris. This is the most massive dwarf planet in the outer solar system, right? And you can see it's moving between these three images. And so we're really looking for the object to move, right? And stars here are staying stationary. So again, planets being the wanderers, again, how they got their names, that again, right, we're looking for solar system objects by looking at how they move. And a lot of times we use the parallax effect where we're letting these objects, by watching them move, based on the Earth's motion, boosting them along. And even in this image, you might notice this blip here that appears and then disappears. That's actually an asteroid. So between these images that are taken about an hour and a half apart, the asteroids move so fast it's out of the frame, but the more distant objects in the outer solar system are moving slower. And so again, just by looking at what things have changed in the image and how fast they're moving, we can figure out where they are in the solar system and then study both their sizes, sometimes their compositions, whether they're cometary, whether they are fuzzy in essence, if they have a coma, and their orbits. And so all of these properties can tell us a lot about how the solar system formed and evolved. So I just wanted to give you a brief tour of the solar system and show this is all the known asteroids. So that the orbits here for the terrestrial planets, getting all the way out to Jupiter's orbit, and every other colored dot on this is an asteroid or a near-Earth object that we know of that's been discovered and cataloged. So there's a lot that we know of, and this is looking out in the outer solar system, more the region that I study. So again, the circles here, the cyan circles, are showing you the orbits of the giant planets. And then every dot on there is a Centaur or a Kuiper belt object or a comet. And again, Pluto is in this ensemble of objects beyond Neptune in what we call the Kuiper belt. And we know about 4,000 objects like Pluto in the outer solar system. So again, I always joke when people say, what about Pluto? I'm like, it went home to the rest of the family, just like Ceres went home to the rest of the asteroid belt, right? Just because it's not a planet doesn't make it not interesting. And that knowing 4,000 objects, we've learned a lot about the outer solar system, and having, large number of asteroids, we've really been able to do things. And so I just want to highlight that by showing you the structure of the Kuiper belt. And so in this plot, I'm plotting the semi-major axis versus eccentricity, so how elliptical the orbits are. And again, here's Pluto Neptune on a very circular orbit. And everything afterwards has in some way sculpted by Neptune. And so you see these fingers that sort of stand up in eccentricity. These are mean motion resonances. So these are objects that are locked in a dance with Neptune that causes them to orbit in integral periods to Neptune. So these are the Plutinos, including Pluto. They orbit twice every time Neptune goes 3 times. And the 2 to 1 mean motion residence. They orbit once every time Neptune does. And this protects them from, although these objects cross Neptune's orbit, they're always on the other side of the solar system when Neptune's nearby, so they don't get scattered. But you see there's a large number of objects that have semi-major axes and large eccentricities. And these objects have actually been scattered and gravitationally interacted with Neptune, and that's caused their orbits to change and elongate. And so this entire region has had some structure from interacting with Neptune. There's also a cold classical belt we call here, which is very low inclination, very circular orbits. And we think these objects formed in place, and that everything else that has higher eccentricities was actually in place during Neptune migration. And just to show you this in a different way, where this is semi-major axis versus inclination. So again, how inclined the orbit is to the basically effectively the plane of the Earth's orbit. Again, you see that there's sort of a clump of objects that we call these co-classicals and everything else that seem to have pumped up inclinations or higher inclinations. And again, we think that all those objects were emplaced by giant planet migration. And so the story that we've learned from studying the small bodies has been that the giant planets didn't form where they are now. They've actually moved. So Jupiter's moved inward, and by scattering planetesimals, Jupiter moved inward, and Saturn, Uranus, and Neptune moved outward, depositing objects into the Kuiper belts, leaving that cold population that was probably primordial, and then the rest of the objects that have actually formed more inward, including Pluto and the large dwarf planets in the outer solar system, and putting them out where the Kuiper belt is today. And that this process is what formed the Oort cloud, where is a source of our long period comets. And so comet NEOIs is probably from one of these populations, whether it's from the Kuiper belt or from the Oort cloud, which is exciting. And again, so by studying even these new new objects or ones that are coming more inward, we have connections to things that are further out. So the Rubin Observatory is really going to transform what we do for small body science. It's going to be 5 million small bodies, 1 billion observations effectively. And so just to give you a scale, why I'm really excited about it is that, you know, we know of 20,000 currently near-Earth objects. We're going to discover 200,000 with LSST. We're going to discover 5 million asteroids. And for me, you know, we know about 3,000, 4,000 Kuiper belt objects. We're going to learn about 40,000. And I've been struggling to even figure out how do you plot 40,000 orbits and what things you can learn from that. Well, we've already learned from 3,000 is a lot about Neptune's migration, what happens when you have 40,000. And we're going to discover, you know, about 10,000 comets, and even a few interstellar objects like Oumuamua and comet Borisov. So I just want to highlight that LSST is providing us with these moving object detections. So there's actually this pipeline that's going to be running and actually looking at those images to see when things have changed and sort of link those little fuzzy blobs as they move across the sky and provide us astronomers the positions and the orbits of these objects and their brightnesses in each of the 5 bands that LSST will be observing in. And so it's really important for finding near-Earth objects. We're going to be able to look at some of these populations. I'm just showing again just some estimates of for given brightnesses of these objects. But the idea being is that we're going to, you know, be able to find lots of near-Earth objects that potentially could hit Earth and others that won't, be able to study this population that comes close by. We're going to find 5 million main belt asteroids. And just again, this is versus absolute magnitude. So if I took the object and moved it to 1 AU, what would its brightness be? But the idea is that, again, over a size range of different sizes, we're going to get, you know, thousands of objects and, you know, over 5 million in total. And so again, we're going to be able to do precise astrometry, get good orbits, look for families, collisional families, all these kind of things that we've done in small scale, but now by having so many more objects, we're really going to be able to dive into. Some of the exciting things that LSST will do is there's objects called main belt comets and active asteroids. So these are asteroids that start to go bump in the night. They start outgassing, at least in terms of dust. And we think that means that there's some kind of volatile driving it, maybe water ice. And others that seem to have collided with an object and produced dust hails. And even some that have probably spun up rapidly and now are breaking apart, and that's why you're seeing dust. And so there's a hint that objects that are really main belt comets, where we think it's buried water ice that is being sublimated and causing what looks like cometary activity, has some correlation with their orbital angle in Jupiter. And so there's only about 12 to 15 known main belt comets, but LSST is going to find an order of magnitude more of these, and things like this object here that looks like it was a collision. You sort of see this X feature. And so the thought is that there's some object that can be and hit it and produce causing the dust tail to be produced. So again, by having these large number of objects and having so many observations with LSST monitoring the sky nightly for solar system objects, we'll be able to know when these objects go off. When we first start to see cometary activity, and slew our telescopes and see how this evolves and pick out which ones are, we think, due to water ice, and do we see this correlation with Jupiter's orbit, or are they things that might be collisions, and learn more about what's going on in collisions in the main belt asteroid. And this is interesting because this might be a potential source for water on Earth. If there's buried water, a significant amount of water ice stored in asteroids in the main belt, maybe this is another way that water was deposited on Earth through something like some objects like this. Also, Trojans, which are in a 1-to-1 mean motion resonance with Neptune. There's also Jupiter Trojans, and most of the giant planets have them. We're in a conundrum right now where when we study them, there's not a large number of them, but we find that they're mostly sort of have these G-R, so G-band versus R-band optical colors that tend to be down here, very neutral, and then we know of one that's very red. And we don't 100% know why, and it seems to be very high inclination. And so maybe it has something to do with collisions, and so it's high up, and so maybe it doesn't collide with the disk very often of debris. We don't know. And so the Rubin Observatory is going to find us, at least an order of magnitude more objects. And so we're really excited as a community to learn what is just a color distribution of these objects. Are they mostly neutral, or are there very high inclination red objects, and does that tell us something about their formation, or maybe about the story about Neptune's migration? The other thing that I think will be answered is, what about Planet 9? There's been discussion a lot about there being a distant planet beyond 200 AU. Although the main moving object pipeline won't be able to do this, it only finds motion within a single night. People in the community will be writing pipelines to extend that and mine the Rubin Observatory data to look for motion further than that, to potentially find or confirm or deny whether there's a giant planet beyond Neptune that is controlling sort of the orientation of orbits of very, very distant objects. And I think there's still debate in the community of whether we're really seeing this orbital alignment of these very distant objects, which would mean that they're all seem to be clustered in one direction on the sky where they come to their closest approach. And the only thing that could do that in the known architecture of the solar system would be an additional planet on a eccentric orbit. But there's a lot of contention about how you include all biases from different surveys as you combine them on the sky right now. And one large survey that is uniform and well-known detection efficiencies is going to help answer this question. So it's one of the things I'm personally excited about, is that Rubin Observatory will play a role in this. And also, we've talked about comets in terms of NEO-wise, but we just recently had last year comet Borisov come by from the interstellar space. And so these are planetesimals that were formed around other stars that are streaming through our solar system that we can study in the same way we reach out and touch the planetesimals in our own solar system and compare them and see how they're similar or different, and really try to understand the extremes of planet formation on these really small scales. And so again, these objects come by fairly quickly. So Oumuamua had about 2 weeks that the community could observe it on telescopes around the world. Borisov had a couple months where that was doable, and went from north to south. So there's a point where northern telescopes could reach it, then southern telescopes. But again, studying all the properties between how fast these objects are rotating, how big they are, what are their surface compositions, whether they're outgassing, whether they exhibit cometary behavior, can all tell us things about how, where these objects formed in their own parent solar systems, and how does that compare to the story we know about our solar system. And again, just between these two interstellar objects, Oumuamua is very point-like. So you can probably see here, it looks pretty much like a star. There's nothing around it. You look at Borisov, and these are stars, but they're streaked because we're tracking at the rate of the object. But there's this fuzzy tail, right? It is a comet. It's directly outgassing significantly. And so already the two interstellar objects are like cats, right? They're very different in their behavior. And so having, we expect that Rubin Observatory will detect a few a year. So just finding these new, objects every year is going to really open up with the start of Rubin Observatory operations. And I think, again, really explore whether what we know about our own solar system, how well does that apply to other planetary systems? And I just want to highlight, we talk a lot about, you know, at least I do, about asteroids and Kuiper belt objects, but comets is also something that Rubin Observatory will do a lot of. It's going to monitor the sky for 10 years. It's going to find lots of objects that are coming just close enough in for us to be able to see them that are starting to outgas from both the Oort cloud and objects leaking in from the Kuiper belts. And one of the exciting things is that there's synergies with, you know, space-based missions. So I'm part of the Comet Interceptor team, and Comet Interceptor is an ESA mission that is designed to go fly by a comet, and its target isn't known. So the idea is it's going to launch in 2028. It's going to sit at the Earth Sun L2 point, waiting for a reachable comet. And hopefully we'll know about the target ahead of time, but the best candidate survey to find a new comet coming into the solar system or potentially an interstellar object is the Rubin Observatory. And so we're preparing as a team as well as the community to expect that Rubin Observatory is going to be the telescope that finds the target that likely Comet Interceptor will go to. So it's a really exciting mission in that it's the first mission that doesn't have a designated target, right, when it's being designed. It has, you know, it has a general idea and they're making conditions for it, but we don't know the name of the object or its orbit that it's going to be going to. And that Rubin Observatory is being marked as the most likely candidate survey to find its candidate. And I just want to highlight, you're seeing all these tools about visualizations. We as a community of scientists are also trying to learn and do this. And so I just wanted to point out some things that I did a month ago, was that we just got our first simulated planetary database from the Rubin Observatory. So this is a simulated database of detections from a run of their simulator with the moving object detection pipeline run with it. And so they took their sky survey, they populated it with what we know about the populations of the outer solar system, inner solar system, and then gave us the database that it would look like if we had been a year in on the survey. And so this is how, you know, figuring how to plot 40,000 points in orbit is challenging. It's not something I've done before. And so this is one of the things that I was learning is how do you plot when you have that many data points? And this is actually 40,000 Kuiper belt objects. This is showing some major axis versus inclination. So again, that sort of plot I had showed earlier, but each one of these points is a simulated Rubin Observatory detection. And so there's just so many objects that I think you saw that plot before, but just how filled it is. And again, just showing you that in semi-major axis versus eccentricity, right? It just zooms so far out because of so many detections and how far they go out. But same thing, we as a community are still learning how do you visualize and then how do you pull that information out when you have so many objects. So this is just a different way of viewing that in terms of semi-major axis versus inclination, sort of bidding in a histogram. And again, you can start seeing those resonant fingers sort of popping out again in inclination. As well as other structure that we know is within the Kuiper belt, but is much harder to see in a simple plot. And so again, by having so many objects, we're going to be able to start revealing this. And so as a community, we're still learning how do we display and dive through this amazing and huge data set that's unprecedented compared to what we've been using for decades before. So I really just want to end with that and say, you know, really every solar system population is going to have large numbers of increases in the number of objects, light curves. We're going to figure out rotation of these objects and how they're rotating, how fast they're rotating, a little bit about composition from the multiple filters that we're going to be observing. And so it's really going to be an exciting time, and that now the community is preparing for getting ready for first light, and there's going to be lots more to come once the observatory is operational. And so with that, I'm happy to take any questions.
Thank you, Dr. Schwamb. We do have a number of questions in the chat box, so I'll start sharing them with you. First from Ken, actually no, from Mark. What is the magnitude of the most Kuiper belt objects?
It varies. So the brightest is 14th, which is Pluto. The objects that can be detected with about a 1 to 2 meter is about 20th magnitude, 21st. 8 meters can see about 25th magnitude. So that's about Rubin Observatory, I think gets a 24.5 magnitude in our band. So we're getting pretty faint. Again, 200 kilometers, about the size of these objects at about 40, 50 AU.
Okay, so from Mark, there are a couple of additional questions, and this was from earlier in your talk. It said, he asked, does the graph show that there is another undiscovered planet? And can LSST discover bodies in the Oort cloud?
So we can't see to the Oort cloud directly. It's too far away. So even the most distant Kuiper belt object. So a planet at about 200 AU is about 20, could be, is about 23rd magnitude. So getting out to about 20,000 AU is just not feasible with an 8-meter telescope. But we can infer a lot about the Oort cloud from the things that are coming inward, right? So the known long period comets, we know that the Oort cloud is a spherical shell. That's what we're getting. And that we know for short period comets, actually, they come from a disk, which is actually the Kuiper belt. Is one of the reasons why people started looking in the 90s for the Kuiper belt out by Pluto, because we knew there had to be some disk-like structure providing the inclinations for the short period comets. In terms of thinking about Planet 9, yeah, there's this debate about, we notice that all these very distant objects that appear to be detached from Neptune have this closest approach around the same spot in the sky. And you'd expect from the giant planets that actually that this position would diffuse around, and so that all these orbits would actually be randomized. And we do see that everywhere else in the solar system except here. And there's an argument about whether it's the fact that they're so far away, and so it's hard to see them. And so are we just seeing this because it's a combination of survey effects, like the other part of the sky where you might look, where it'd be opposite is where the galactic plane is, which is large star density. So you might not want, it's hard to look there in ways that most astronomers do, where you take an image, look at the next image and see what moved. When the star backgrounds are so high, you actually have to subtract the images off each other, and that can be sometimes challenging. So there's still a lot of factors, I think, in here to say whether or not we know there's a planet out there, but the likelihood is, if the models are right in terms of the theory that's been proposed, River Observatory should see Planet 9. And if it doesn't, it's going to at least be able to see this orientation, right? And that we're seeing all these distant objects aligned this way. And if it doesn't, and we know exactly where River Observatory pointed, we can actually put models through and see if it matches that the simulated detections and our real detections, whether they align and match what you'd expect if there was a ninth planet. Planetary mass beyond Neptune.
Okay, we're pressed for time and we have to move on to the next piece, but I did capture the additional questions that are in the chat box, and I'll share those with artists who will share them with you.
Great.
Okay, thank you. Thank you very much.
Well, I want to also add my thanks. That to me, this is a personally fascinating talk. I have a soft spot in my heart for the solar system objects, and so I really appreciate this, and thank you, Meg. And if you would like to stick around, you're welcome, but if you need to leave, we certainly understand that as well. And just for the group, I wanted to let everyone know that Meg did share her slides, so as we've been doing, I will post her presentation after we're done here today. So thank you very much.